This is my charge to describe what Fermi has done and to speculate on what Fermi may do next. Do I get 15 minutes? I mean, I know that if we stick to time, I'm done 3 minutes from now. What do I get? I'll try to make it entertaining enough that you guys can stick through this with a coffee in the offing as soon as I'm done. So here we go. I first got to say that Fermi, of course, has been an outstanding success. John already alluded to this. You started with the pre-Fermi observations giving us only a handful of objects, and we've had a large number of discoveries, sort of equally spread between classical radio-detected pulsars, objects seen only in the gamma rays, and millisecond pulsars. A bunch of other millisecond pulsars have been found in the direction of Fermi sources, and as time goes on and we fix the ephemerides, they fold up and we see their pulse in the gamma rays. So the official number in the second pulsar catalog is about 117. 125 have been announced, but I can say with high internal confidence that we will break 150 by the year's end. So I think that there's more to come. What have we learned from this harvest of objects? I need to summarize that first. Well, I think the first basic thing is for the young, energetic pulsars, the pattern that I was advocating during the egret era seems to be really robust. What you see when you see a young, energetic, spin-powered pulsar is a double caustic, a double gamma ray pulse from a hollow cone from the hemisphere opposite the radio. That's the main story. There are exceptions, and the exceptions are interesting, but the phenomenology is really robust. However, the physics is, I would argue, less than compelling, and John would say disgusting. So the thing that backs it up, this picture, is the classic vacuum-like region where you're going to have large E-parallel and high particle acceleration. That needs a lot of work if we're going to make any interpretation based on that. But we need to go on and actually see what this phenomenology tells us about the population of objects themselves. I need to say something about the really great discovery of Fermi of the large number of millisecond pulsars that are seen pulsing in the gamma rays. What's the main thing we get from those? Well, I think it's really this. In this diagram you already showed where you compare the gamma ray power to the spin-down luminosity, the millisecond pulsars cluster in this region. This line is 100% efficiency of turning spin power into gamma rays. The millisecond pulsars are remarkably efficient. Now look, by the standards of what we learned about neutron stars, everything's efficient. Gamma rays are great because they are tracing the energetics of the machine itself. We are almost certainly dealing with radiation reaction-limited particles. And so when we understand the gamma rays, we're going to understand the electrodynamics in a serious way. That's one of the main lessons. Now, the pattern I argued for the young pulsars is robust and pretty appealing. For the millisecond pulsars, things are much more complicated when you look at the pulses. It's clear that you're accelerating things from right down near the surface, that it's not all out near the light cylinder, as John already mentioned we see for the younger pulsars. Some objects seem to be pair-star throughout. Alice and her colleagues have kind of made that point strongly. Well, look. Near the surface in the light cylinder, it's all in the same place for a millisecond pulsar, so the distinction is somewhat less clear. Okay, so that's what we learned there. I wanted to spend one slide, if I can keep this thing working in the forward direction, just mentioning, for heaven's sake, calm down. Let's stop for a second. Yeah. So a very simple dipole magnetosphere geometry works surprisingly well, almost disturbingly well for this phenomenology. Why is that? There's a simple argument that I'd like to present to you that I think is worth remembering. Look, at least for the young pulsars, the thing is that the light cylinder, as a function of the spin period, increases the number of neutron star radii at the light cylinder increases like this. If you have emission from near the light cylinders, as you do from the young lap pulsars, it's many neutron star radii away, the higher order multiples are gone. So dipoles work. If it's inside the light cylinder, the great complexity associated with currents and other magnetospheric perturbations are relatively unimportant. The millisecond pulsars are almost certainly more complicated because you're right at the zone where everything matters. Currents, surface multipoles, it's all important. So complexity for the millisecond pulsar, simplicity for the young ones is not unexpected. Okay, I need a word or two about the population. Given the large number of pulsars discovered, as John said, you can finally start to say things about the young neutron star and millisecond pulsar population as a whole. Here's the main lessons we get. Looking down on the Milky Way galaxy, here's our current second pulsar catalog sample of objects. 3 classes here. There's the classic radio loud pulsars in green. There's the radio quiet pulsars in blue. And there's the millisecond pulsars. If you look at a flux-limited sample, or a volume-limited sample is probably even more useful, there's one really useful factoid that comes out, and that is that the radio quiet pulsars outnumber the radio loud pulsars by 2 to 1. The gamma ray beam is larger than the classical radio beam, substantially. And so when you take a census of the young neutron stars in the galaxy, the way to do it is in the gamma rays. That's where you find a much more fair and much more complete sample of the young energetic objects. That's not true for the millisecond pulsars. In fact, to date, there is no radio quiet millisecond pulsar. Now, if you do that sort of population synthesis as we have, you'll find something very interesting. If you take the rate of energetic lap pulsars birth in the galaxy, it's about 2 per 100 years. It's a very large fraction, and in fact, at least half of the core collapse rate in the local universe. So arguments that there are vast numbers of neutron stars that are not classical energetic spin-powered pulsars are very difficult to accommodate. There's certainly some, but they don't greatly outnumber the classical neutron stars. Fermi's made that pretty clear. Now, it's the oddballs that are probably going to teach us more than the bulk of the population. I want to just mention 4 things quickly. We won't have time to talk about them. But the Crab pulsar being detected at greater than 100 JeV, it's Compton processes. By the way, I think most of us knew this was going to happen, but Maxim Ludikov has made a big argument about this, and I think really forced us to face this very clearly, that there must be some Compton emission for some neutron stars. We kind of expect it for most. Interesting recent discovery in the Fermi data. One of the pulsars, Gamma Cygni, the pulsar in Gamma Cygni is actually changing slightly its light curve, and that light curve, gamma ray light curve change is associated with spin down variation changes. Okay, so we have an example where the geometry is changing slightly, and that does change the torque. An interesting project that Matthew Kerr is undergoing is a survey of the young pulsars and their glitching behavior. Fermi is an all-sky monitor. It sees everything all the time. This will be the first example of a uniform, flux-limited list of all glitches down to the sensitivity of the instrument. The reason I'm bringing up all these things is that the subject of this session, the physics of neutron stars, is going to be advanced by Fermi in a number of ways. And this very large sample is letting us get some really quantitative discussion of things like glitch behavior, currents in the magnetosphere and their variation, and radiation processes at very high energies. Okay, so that's it for the quick summary of what Fermi's done. What's it going to do next? Well, take a look at this quote, and that means I really can't say anything with confidence. But I still have been asked to do so, so let me do what I can. The first thing I've learned from the Fermi population is the gamma rays are a signpost to large particle acceleration. They're probably pair-starved regions in pulsar magnetospheres, at least that's my view. We've also learned that the gamma ray beam is wider than the classical radio beam by at least a factor of 2 for the young pulsars. And of course, we know it's gamma rays, so the radiation is penetrating. So my main prediction is not all that far out on a limb. It's that we will find, using Fermi, pulsars that are wonderful, that are misaligned and deeply buried. Sorry, Rosalba, we haven't found any magnetars, and I expect we won't. I'll be really surprised if we do. We haven't found any accretion-powered systems. I'll be surprised if I do. In both those cases, its pairs are going to poison the magnetospheres. You shouldn't make gamma rays. So what about the next LAT pulsar discoveries? You might very well ask, okay, you've got 150. Who cares about the next one? The point is that the LAT is actually pointing us to really unusual neutron stars. And by chasing up the sources the LAT find, I think we're going to find exciting things that actually address many of the topics in this session. Now, I think I'm going to have to plunge right on and just mention what those topics are, and I can't talk about the physics we're learning about. If we get a chance in the discussion afterwards, ask us and maybe we can discuss it a bit. So what are you going to do to study the LAT sources? Here's the first category. Studying the very bright unidentified sources. One interesting contrast to something Neil Garrell said yesterday is, at least for the bright sources, we know what they are, almost all of them. They're blazars and spin-powered pulsars. In fact, when I started this project, out of the brightest 250, there were only 6 that they didn't know what they are. We in fact found that 2, and increasing, fraction of those 6 are very unusual spin-powered neutron stars, millisecond pulsars deeply buried in binaries. Makes perfect sense. The binary wind prevented you from finding them in the radio, and the Doppler shifts prevented you from finding them directly in the gamma ray. Now, that's fun, but what's physics is that these objects are extreme. They're objects that have accreted immense amounts of matter, and the best kinematic measurements we made to date suggest that they are very, very heavy, heavier than 2 solar masses. As you heard in Andrew's talk, 2 solar masses already constrains a lot of classical thinking about the neutron star interior. At 2.4, they're going to have their backs up against the wall. If we can make strong measurements of the lower limit of the mass of these objects, then I think I expect that we will have very strong constraints on the state of nuclear matter at high densities, probably more powerful these maximum mass probes than many of the other observations that have been made. If I get a chance, I'll talk more about that later. Okay, onward. That's the bright sources. We should also continue to search down the faint sources because, as I think Jim will come on to later, there's a lot of interesting things that can be done with radio pulsars. In particular, GR tests and tight binaries, searching for gravity waves. And here's the thing. As you work down in the gamma ray flux, you find remarkably that the newly discovered faint gamma ray sources are often quite bright in the radio. They're wonderful sources for doing many of the classic things we do with millisecond radio pulsars. So that's all good. Another frontier are the binary sources. I would argue that the things that we see in the sky that are associated with massive star binaries are probably pulsars as well. This remains to be proved. And given that my time is up, it's time to flip right through the last few things, and that is that we can also look for new accelerators in individual bright pulsars. Ask me about that later if we get a chance. And finally, we can look at the product of pulsars, the E plus E minus that the pulsars eject. Here's an interesting figure. Those of you who are interested in dark matter are excited about the possibility that the local electron-positron excess, seen originally by Pamela and then Fermi and now AMS, may have something to do with dark matter, but it may be astrophysical as well. We know that pulsars produce such power. Now, this figure shows you the local environment, 1/2 a kiloparsec, 1 kiloparsec around the sun. In red are the classical known radio pulsars. The dots are proportional to their the flux at Earth, if it were isotropic, of E plus E minus arriving at Earth. So Vela dominates. But interestingly enough, take a look at these blue guys discovered by Fermi. A large fraction of the local power in E plus E minus wasn't even known before Fermi launched. Keep in mind that the flux of electrons and positrons at Earth depend intimately on the magnetic field structure. You will see that the flux that we experience here of E plus E minus may be entirely tied to objects that were not known 5 years ago before Fermi launched. So it's important that we chase that down. I got to my last slide, and I'm only about a minute over. You've got coffee in the offing, so let me just conclude by giving you these takeaways. Fermi's really shown you the dominant photon emission from spin-powered objects, and it's a way to understand their physics. There's a good phenomenology in place, which tells us something about how the young pulsars produce beams of gamma rays, but there's lots of room to improve physics, and so there's lots of work still to do. The simple observational fact that you've got these wide beams of gamma rays and gamma rays are penetrating means that we will, with Fermi, discover deeply buried and exotic pulsars. I would like to argue that those deeply buried exotic pulsars are exactly the ones where you need to do interesting physics. So pulsars as a physics lab is something that Fermi is going to make a lot of progress on. Keep tuned. Thank you.
SUGX-1 probably also has gamma ray emission. We had a paper recently, first author was Bodegi, where we reported Fermi detection of gamma ray emission from SUGX-1. And I don't think SUGX-1 is a pulsar.
I'd be willing to agree that SUGX-1 is not. Now, you noticed I had a little bullet there where I said that no accretion power binaries would be seen. But I wisely added a caveat, which is that if you have a jet-dominated phase, just like an AGN, it may be possible to have a low pair region where you can have some particle acceleration to gamma ray energies. I wouldn't be dramatically surprised if SUGX-1 had a weak gamma ray signal, but the sort of strong magnetospheric signals that we see from pulsars, I think you got to be pair-starved to do that.
Roger, you pointed out that the birth rate of the LAT pulsars is comparable to the total core collapse rate. So I was just wondering, from the point of view of just looking at the gamma ray beam pattern, does that predict that you should be seeing all the pulsars, or are we still missing some?
Yeah, all is too strong. From the gamma ray beam pattern, you can, of course, calculate the fraction that miss on the sky. And indeed, there are, and should be, a small number of so-called isolated neutron stars. RxJ 1856.5 is probably the premier local example. But that number is small, and I think my main point is that the gamma ray beam is both broader and, in some sense, more calculable than the radio beam. And so our ability to take the observed population and correct back to the underlying neutron star distribution, I would argue, is substantially more refined. At least we can make a better estimate. And those calculations do include that the small number of unseen, not gamma, not radio sources.